All right, here's our next speaker, online adaptation of terrain-aware dynamics. Let's make sure the mic works first.
Okay, can everyone hear me? Okay, great. All right, so how's everyone doing today? My name is Adam Thorpe. I'm a postdoc at the University of Texas at Austin, and today I'm going to be talking about online adaptation of terrain-aware dynamics. Ooh. Okay, so for off-road robotics, what we ultimately want is a robot that's going to handle a wide variety of scenarios and terrains that it's going to encounter in the real world. So for example, we want to be able to handle something like this rather than just these idealized uniform scenarios where we've got a nice groomed gravel trail or some sort of just flat patch of grass. We want to be able to handle dense vegetation, off-road terrains, routes, things like that. The challenge is that real-world terrain varies quite a bit. And so here's an example from a recent data collection day that we had at UT, driving through this dense cluttered environment. Our vision is to create systems that can adapt their behavior on the fly to these complex terrains without having to manually predefine or retrain for each scenario. So the problem is, how can we adapt to different terrains? An initial thought might be to define a model for each of the different terrains. For instance, we have a model for grass, we have a model for dirt and mud, and then we switch between them at runtime. But this assumes that we have nice clean boundaries between all of these different terrains. And the problem is that we may not know how the system operates on mixed terrains, for example, muddy grass. And there are also just simply too many terrains to enumerate. This is a losing battle, and it's just not practical. So instead, what we need is a way to adapt to a continuum or a spectrum of different terrains that we might encounter in the real world. So a lot of traditional off-road autonomy stacks use perception and mapping to build semantic cost maps, essentially assigning risk to terrain based on visual or semantic cues. And this helps planners figure out what regions to avoid, but it doesn't really tell them how the vehicle will drive through the terrain. And there's a little bit of a gap here. We need models, we need models that are able to adapt to the different terrains that tell us how the robot will move, not just where it should or shouldn't go. Okay, so here's why this matters. In this video, the robot's navigating to a goal through some buildings here, and we've artificially modified the terrain to make it slippery like ice, so we've reduced the friction of the environment. And without an accurate model of the environment or the terrain, the system would simply crash or spin out, it would hit the obstacles, and it wouldn't reach the goal. So here, what we've done is designed a system to be able to adjust the dynamics of the system to the terrain, enabling it to essentially drift through the buildings and still reach the objective. And this kind of adaptation is critical for downstream performance in scenarios like this. So our ultimate goal is to estimate the dynamics of the system given some historical trajectories of the robot operating on different terrains and given a small amount of online data. So a typical approach might be to learn a neural network model of the system. For instance, a neural ODE, we just parameterize the dynamics via some neural network. But this doesn't have a natural mechanism to adapt to different terrains. So instead, we employ what's called a function encoder. Essentially, we replace this single neural network with a linear combination of neural networks. And each neural network captures features of the terrain. And these coefficients allow us to parameterize the model to the different terrains. We just need to change the coefficients. And this effectively can be viewed as a linear combination of neural ODEs if you just flip the integral and the sum. So it gives you some intuition of what we're going for here. And then once we have this model, we want to be able to plug this into a downstream controller like MPC or MPPI in order to create an accurate model for predicting rollouts or for assessing what the robot is going to be able to, where it's going to go. Okay, so how does this actually work? Offline, we assume that we have a set of trajectories taken of the robot on different terrains. So for instance, we might have trajectories on pavement, grass, and dirt. And then we learn a set of NeuroLoadE basis functions offline, and we're going to use those in our model. Once we've trained on these terrains, the basis functions are fixed. And then online, for some new terrain, all we have to do is compute the coefficients online using some online data. And we use that in our linear combination. And then we can plug this into a downstream controller to get accurate model predictions. Okay, so to make this just a little bit more concrete, here's what the training and adaptation phases look like. So offline, we're effectively training a set of neural network basis functions. You can think of these sort of like vectors in Euclidean space, but here we're talking about functions. So these are actually more like vector fields than just straight vectors. But given some historical data on different terrains, the basis functions learn to reorient themselves to span the different possibilities that it's seen during training. And that means that online, we can fix these basis functions, and then at inference time, all we need to do is compute the coefficients. We just need to compute the alphas in this figure, and we can do that using a small amount of online data. And the important part is that this is incredibly simple to do. We can do this just as a simple least squares procedure. We just need a little bit of online data, and we can compute that very, very easily. So we don't need to retrain any of the basis functions at runtime. Okay, so let's look at some results from simulation. We designed environments where the terrain parameters vary. So we varied the friction of the environment, and we can think of this as kind of like a number line or something like this, where we have a spectrum of different friction parameters. And we tested the model and the downstream control performance in these different environments. And across the board, we can see that the function encoder has better single-step prediction error than just a standard NeuroLoadE. And a big reason for that is that the NeuroLoadE just doesn't have a mechanism to adapt to these different scenarios. So it essentially learns one model for all of them. And then even on these unseen test terrains, we see that there's a little bit of a spike for the NeuroLoadE because it just simply hasn't seen that data before. And then the key result here is that the function encoder has a more accurate prediction performance than the NeuroLoadE on the single step, but also on these multi-step prediction tasks. We see better performance of the function encoder on these unseen test scenarios. And part of that is that essentially what we're doing is we're learning a space of dynamics rather than just trying to fit the data. Okay. These long horizon prediction tasks, by the way, are also exactly what is important for accurate MPPI control. We need to be able to have more accurate rollouts in our predictions. And so this is a big factor of what contributes to our good performance. Okay, so here's a qualitative example. The robot needs to navigate to these different waypoints and then reach the goal. The NeuroLoadE on the left has a mismatch with the true dynamics. Basically, it over or undershoots because it's not able to adapt to the actual terrain that it experiences. And so what that leads to is it collides with the different obstacles, and it just fails to reach the goal. But on the right here, the function encoder adapts the model to the terrain, and so it enables it to drift and navigate through the different waypoints and successfully reach the objective. And again, the big reason for this is that we have accurate model predictions. Okay, so here's another video showing our approach, but now kind of pay attention to how tightly the robot's operating near the obstacles, and notice that the predicted rollouts here in the corner are much more accurate, or are accurate, meaning we can get good control performance navigating through these buildings. These maneuvers kind of rely on the predicted model rollouts being accurate. And this is what enables us to successfully plan in this environment. If the model is wrong, say if you assume that there's too much friction or if you have too much mismatch, the robot would overshoot or collide with the buildings. But here the model is adapted to the low friction surface, and so the controller successfully completes the maneuver. Okay, so looking ahead in ongoing work, we're enabling real-time adaptation. So we're looking to estimate the coefficients via recursive least squares. So what I showed before, we're using least squares, but that assumes that you have some set of data that you can use to compute the coefficients. So to enable this for real online adaptation, what we need to be able to do is estimate those coefficients as we go in response to new data. And so some preliminary results that we have show that we can estimate the accurate dynamics in real time and also adapt to changing environments. For instance, going immediately from pavement to ice, we can see that the model estimate quickly reduces the error and we get an accurate model that we can use for planning. Looking even more ahead, what we want to be able to do is not just do this in a reactive sense. So far, we're using inertial odometry data to be able to predict the dynamics, but we want to be able to do this looking ahead. So the next step is to take this from inertial data to camera data, and to be able to go from camera images, convert these into some form that we can use to extract the terrain properties, feed this into a map that will go from the image all the way to the coefficients of our dynamics model using the function encoder. And so this is future work on how we plan to expand our approach to be able to tackle these other types of challenges. Okay, and with that, I'm going to thank everybody and ask if anybody has any questions.
Thank you very much for the talk. The next talk is me, so if you hate my voice, I apologize. Do we have any questions from the audience?
Yes.
So I guess your idea is to find a linear combination of that, right? I guess this is the question that made people. What if your new terrain is something very different and cannot be expressed as a linear combination of it?
So we are hoping that the unseen terrain is in the span of what you've seen before. So this is an assumption that we have, although we do test for extrapolation outside of what we've seen during training. And we can see that using the geometric properties of the space that we're learning, effectively that we're using basis functions, does allow us to go out of distribution quite a bit. Yeah. Yes.
How robust is it against situations where you have, say, two of your wheels are in dirt and two of your wheels are on pavement, or these kind of hybrid kind of corner cases which come up surprisingly often?
Yeah, so this is something that is a little bit of a challenge. However, I think that the big thing here is that we're not necessarily separating the terrains cleanly. We're kind of assuming that everything is a little bit of a mixture, and the linear combination allows us to account for some of these mixed terrains much easier. Yeah. Okay.
Thank you very much.
Of course.
One more round of applause.